So, we said therefore, what is the way forward to implement a gate and more? So, to implement a good gate which is of the order of the pulse itself, we can essentially go back to our good old tricks of doing interferometry and delays. Maybe I touched something. Okay. So, we can go back to the scenario of introducing a delay, producing a delay as best as we can, and use a function that is similar to the pulse itself, which is the pulse itself. So, take tau, make a delay. So, as always, as the first part of the setup is identical to the Michelson arrangement we had earlier. A beam comes, splits through a beam splitter, goes through a and goes through a delay stage and overlaps with itself. What happened? Just a pause. Is the screen flickering too often? More than I thought. Okay. The screen is pulsing. Okay. Now let me see. Let's see. I think Arun is. If it happens again, we'll take a break. We will do something about it. So, in any case, the strategy therefore is to come in with two beams, and here we are doing something, implementing a technique which we call frequency resolved optical gating. Remember that there is a Fourier transform involved in this entire process, right. So, the Fourier transform requires that we throw away the earlier spectrally insensitive detector which we had, which was like a photodiode, and introduce here a spectrometer. Okay. The spectrometer is placed in the path of the signal which we create in order to measure its spectrum. The measurement of a spectrum is essentially this integral, that is mod square of the Fourier transform of the signal whose spectrum we would like to record. Okay. So, that is what it is. We will make a pause. Just call Arun. The trick therefore now is to create a delay tau, okay, and you create a gating function. The gating function, we realized a good gating function is something of the order of the pulse itself. Here this is not the field of the pulse, this is the intensity envelope of the pulse. The mod square of E of t is simply I of t, right, or I of t minus tau in this case. So, this implementation of this gated technique of building a spectrogram is what is exploiting the intensity envelope of the pulse to do the function of a gate, right. So, take that. What is the idea of doing this measurement? Take one of these beams, one of the two pieces of the delayed beam. Here this is E of t minus tau is essentially the gating piece of the beam. So, this goes through the delay stage. You move the delay back and forth with respect to the pulse that is coming through this way. You create a delay. In reality, there may be a little detour that this pulse also makes, so that we equalize the arms of the interferometer and we are able to introduce positive and negative delays and so on. That is a matter of technical detail. We have examined this earlier in some detail. Now, E of t minus tau is the gating function. This goes through a polarization rotator, a half wave plate, which rotates the polarization of this initially linearly polarized pulse to an angle which is 45 degrees with respect to that of the input or incident angle. So, between either side of this wave plate, the polarization has been rotated by 45 degrees. Now, the lens focuses these two pulses, okay, onto a nonlinear medium which is glass. Okay. Now, in the one of the in the other arm where the signal field, the waveform which we need to determine is present, we take this as the test signal, pass this through a polarizer such as a polarizing beam splitter, deliberately introduce a polarizer so that we can improve the contrast of our measurement. That is one reason. Even if you start with a linearly polarized pulse, introduce a polarizer, that is what this scheme elucidates. Now, in the nonlinear medium, spatially and temporally overlap these two pulses and scan the delay. What is the signal we are measuring? On the path of the waveform which we are trying to measure, which is this one, this is the path of the waveform we are out to measure here, introduce another polarizing beam splitter which will reflect the linearly polarized pulse, okay, entirely. This beam splitter splits, takes any pulse. Let us assume that this is vertically polarized. This beam splitter reflects the vertically polarized piece of light and allows the horizontally polarized component. It is a polarizing beam splitter. So, these two beam splitters are key elements, they play a key role in the strategy. Here introduce a nonlinear medium. What do we mean by this nonlinear medium? Here we exploit the third order nonlinearity, the Kerr effect, chi3. We have a medium with appreciable chi3 which could even be glass. What do we mean by appreciable chi3? A medium which for the intensity of the pulses we are using essentially has appreciable reasonable chi3, so that nonlinear behavior, nonlinear optical phenomena manifest, and in this case particularly the Kerr effect, okay, which is in some sense captured in the intensity dependent refractive index N2. But what does this device do? Now, in the presence of both the pulses, when they have a reasonable overlap in the medium, when they have a reasonable overlap in the medium, what happens is that this pulse, which is whose polarization is rotated by 45 degrees to the other, okay, this pulse, the gate pulse, is a combination of, you can say, E parallel, a component parallel to the initial pulse, and E perpendicular. Now, the test pulse or the unknown waveform E of t, this one's electric field, let us call this E test of t, essentially is polarized about E parallel. It does not have any perpendicular component. Initially, E perpendicular was nothing, okay, the input. The output on the other hand E out, maybe I should call this, let me write this down more clearly for the E in and E out. for the test pulse, the input is all E parallel in, there is no vector sign, all of the amplitude was exhausted in the first component. Here in the output we have E out parallel, E parallel hat, E out perpendicular, E perpendicular hat. Where did this part come from? This was due to the Kerr rotation induced by the gating pulse. The gate pulse's role is Kerr effect or Kerr rotation of E of t. So, we exploit the polarization. So, this is a form of polarization gate, right. This is a polarization gate. The gate is polarization based, but we could also generate a gate in principle out of the second harmonic generation process. The key is nonlinearity, right. Exploit a nonlinearity to gate, that is what is going to do the gating action. But then remember, the most important thing is, do not just put a photodetector, introduce a spectrometer. Introduce a spectrometer and measure the spectrum for every delay, right. So, it is an omega tau measurement, spectrum and delay. So, that is the spectrogram. So, this is the way we realize creation and measurement of a spectrogram, but that is half the story. We have measured the spectrogram using this technique, which is appropriately called, it is a gating technique, it is an optical gating technique, and because it is a spectrum is frequency resolved, it is a frequency resolved optical gating technique or a frog, right. So, it has amphibians have entered, there is an amphibian name to this, and therefore, many techniques suitably have continued to have names, as we might see some of them later, such as tadpole or grenouille. Oh, it is a French word. So, grenouille or grenouille, I do not know. Does anyone take any French lessons here? Anybody? I think it is grenouille. Yeah. So, such methods, but they are variants of frog. Both tadpole and grenouille are variants of the technique called frog, right. So, that is the interesting and important aspect of doing frequency resolved optical gating. So, what is going to happen? The point is, for a nice Gaussian pulse, it is easy to, or it is easier relatively to visualize the gating process. The gating process essentially relies on the fact that we generate a signal when the waveform and the gate are overlapped, which is this region. From this region of overlap, we generate a signal, okay. That is mod square of E of t minus tau. This intensity function gates out a piece of E of t. It simply gates out this piece of E of t. But then this gate is going to move, is going to scan the span of this pulse and more, right. The gate is on wheels, it is going to scan this and give us a full spectrogram, right. And nonlinear processes come and aid us in this game. So, but what do we get out of the frog measurement? Well, we get exactly what we were asking for. We get the time frequency maps, the spectrogram, which of course looks like what we were discussing earlier. The frog trace of a negatively chirped pulse, a positively chirped pulse and an unchirped pulse look like this. Okay. So, in all these cases the envelope of the pulse is close to Gaussian, okay, and it is a very well behaved pulse. So, these frog traces also say the same. We will look at frog traces of other kinds of pulses. Now, if a pulse has undergone substantial self phase modulation, remember we discussed self phase modulation earlier, then its frog trace looks very distinct. If there is substantial cubic spectral phase in the pulse, remember that the odd terms in the spectral phase expansion of what we discussed earlier remember that the one of the features of a pulse with third order term which is quadratic chirp, a pulse with a quadratic chirp essentially had a pedestal on one, had a satellite on one side of the pulse. Okay, I have really not done a great job of this. I'll try it out this way. A pulse with a third order spectral phase term. I am just recalling what we had learnt earlier. Essentially had two satellite pulses on one side. You remember this? Whereas an even ordered term like phi 2 or phi 4 term led to pedestals, symmetric pedestals. Even ordered terms led to symmetric structures about what I can designate as a 0 of time, whereas the odd orders were not symmetric, right. So, look at this frog trace here, where the spectral phase is cubic. Okay. The frog trace is reflecting some of that. The spectrum as a function of delay is different. Now, if you have a double pulse, then the frog trace of the double pulse is very different from the autocorrelation. The autocorrelation of such a double pulse, because we may or may not have sufficient resolution to distinguish all the nice features of the double pulse, still look in certain cases as something like a coherent artifact. Looked something like a coherent artifact on top, reflecting the two sharp features, which is the two pulse maxima, two pulses, and the rest was just a pedestal. We can work this out as to why this is happening. Okay, why the pedestal is formed can be also easily worked out. But frog traces are more complex, hence more complex and hence more unique too. That is exactly what we want. We want a unique fingerprint of each of these pulses. But just as in forensic science, the uniqueness of the fingerprint tells you if in a forensically interesting scene There are 2 sets of fingerprints, it tells you there are 2 people, 3 sets, 3 people, 4 sets, 4 people. But that's the problem doesn't get solve itself there. We need to figure out who the people were. That's solving the problem completely. We have not done that yet, but we will do that as we go forward. So, substituting for E signal t of tau in this expression for the frog trace, right. We essentially are able to measure a frog intensity. Frog measurements are intensity measurements, right. As a consequence, now we have got to address the second half of the problem. What is E of t? How do I retrieve this? Okay. In order to know E of t, we need to know the gate. But the technique itself is just the gate, it is optical gating. The implementation of a frog technique, of a frog scenario is an implementation of the gate, nothing else. We used a polarization gate, or we discussed a polarization gate. We can have second harmonic generation as a gate, or third harmonic, or whatever, right. Now, can we get back to the signal E of t from any of this or all of this? What guarantees us this retrieval? Will the retrieval work? Well, we started out after all with the autocorrelation. It was also a delay technique. You may argue that, hey, look, the interferometry was also a gating technique. We gated the pulse with itself. We did not measure its spectrum. We measured a signal that was born out of the overlap, or the gating process of a pulse gating itself out without spectral resolution. There it seemed we had no way to retrieve the pulse. Here, just because I have more information, it is 2 dimensional. The dimensionality coming from t and omega, the 2 variables, the spectral variable and the delay variable. So, I have made it a delay, right. So, for in terms of mathematical equivalent, suppose I have a function of one variable, I could Taylor expand this as and so on. If I have such a function, if I know f0, 1, 2, 3 and I have a procedure for determining as many orders of f as I want to, then I have figured out how to represent this function, or for that matter if it is a polynomial function, right, ax a plus bx plus cx square. Or I have a quadratic equation. Isn't this how we were taught to write quadratic equations? I want to solve for x, right. In the case of a 1D function, I know that this is what? Help me out here. What is the solution of the quadratic equation? Minus b plus minus the square root of b square minus 4ac divided by twice a. So, of course, we learned about this, but something guaranteed us this solution. We knew for whatever reason. But if we had a cubic polynomial, in principle we can still factorize it, right. We can make it x minus alpha, x minus beta, x minus gamma is 0. you can still factorize it. So, there is some underlying mathematical principle which tells us that we can factorize it. Now, how about a 2D polynomial? Do we have a general procedure for solving these 2D polynomial functions? Actually, we do not. We were not taught that because this problem cannot be really solved. Right? Maybe we can do some hit and trial methods, can find solutions once in a while, but maybe it cannot be solved. But looking at it in other things like an optimization sense, maybe we can find some minima of the f of x y function which pretend to be solutions and so on, which is something one can do. But you see that these kind of problems, though in some cases we learned this, we took them for granted to some extent, they always may or may not have solutions. Now, in this case, the point is that we must invert this integral equation and solve for E signal of t, right. And if I know E signal of t and I know the gate function, then I can determine E of t. That is the whole plan. Can we do the inversion? That is the question, right. And E signal of t is essentially this, contains the information of E of t, and knowing the gate in principle for such as for the polarization gate, we have demonstrated here. If I can determine the, let us go a step back, if I measure I of I frog, okay, and I can invert this integral to get E signal of t, I know the gate function, right, then essentially I can retrieve the E of t function, which is my the solution I seek. Now, how is this done? Okay, let us go through all that. What we must maybe appreciate, which I am not going to go into the details of, I gave you a flavor of this in the previous view graph, is the following. The problem is that this 1D phase retrieval, wherein we simply measured the spectrum of the pulse, whether we have a gate here or not is inconsequential. If I simply measured only the spectrum of the pulse, you multiply this pulse with a gate, you do not multiply with a gate or whatever thing you do, if you finally get only the spectrum, okay, S of just the measurand, the measured piece is just a function of one variable, just omega, no idea of the delay or whatever, right. If you do not have the delay, you only have omega, the value of the omega the spectrum here, then it is a 1D problem, and we are trying to retrieve the phase, we are trying to retrieve the spectral phase which is phi of omega, retrieve phi of omega, measure only S of omega, no tau, do not take the tau for granted. If I measured only the spectrum, we know intuitively that we cannot determine E of omega, we cannot determine this, we know this. A practitioner figures this out, but mathematically also, given, if you are given only S of omega, you can fit the, you can invert the S of omega to infinitely many E of t's, because we do not have the knowledge of phi of omega, no delay involved. When we lack spectral phase, we can just map it to a whole set of these, therefore, we do not have what we typically like to call the unique solution. Unique solution cannot be found. This is exactly the problem with trying to solve trying to factorize a function in 2D, we may find a factorization, but that needn't be unique, and so on, right. However, magic happens. We complicated life with going from 1 to 2D. We introduced two variables, one is omega, the other is tau. Does this problem have a unique solution in terms of retrieval? Does the 2D problem have unique retrieval? Now, let us take an example from elsewhere, but possibly related to optics. What is an image? An image essentially is a two-dimensional signal of the electric field, right. It is another matter that what we measure with our eyes. For example, we do not measure the field, we only measure the intensity. So, we measure something which is absolute value square integrated over all of time. But let us mimic the same process as now and pose ourselves the following, right. We take the 2D signal, Fourier transform it using this operation here. This is responsible for the 2D Fourier, but again throw away the phase information. Just this integral without the mod square still contains the phase information. The amplitude, it has an amplitude and a phase. The phase function would have been for this a phi kx ky e to the I phi kx ky multiplied by that would have been the value of the integral alone without the mod square. In mod squaring it, I simply threw away the phase information and got only this. Now, it so turns out that in 2 dimensions, knowing S kx ky, which is the 2-dimensional spectral domain information, although this is a spatial frequency. What is kx? What is ky? These are spatial frequencies where x and y are the variables of interest, all right. X and y are the variables of interest. Now, essentially it so turns out that in the 2D case, we can retrieve essentially one solution. Okay, it turns out that it is possible to retrieve a unique solution. This is actually also related to the fundamental theorem of algebra. The fact that 2D polynomials do not have a unique solution is in some sense also responsible for the fact that this 2D phase retrieval problem has a unique solution or retrieval possible. Ironic it may seem, but that is the underlying math. Okay, we are not going to discuss that, but the point being that we know this from many quarters. A lot of crystallography relies on this. Of course, in crystallography this is even 3D. The structure of the DNA of the ribosome, all this rely on phase retrieval. Remember that, that is what gives us the structure, right.